Okay, now we are ready to move to part number 14, which is about factored geotechnical resistance. And that is the present. That's what everyone should know, and that is what everyone should do. So we're gonna discuss that through the Canadian and the CSA and the H2. And it's very important to understand what does factor geotechnical resistance mean and how you can calculate that part, because that's basically what you recommend to the structural team. So we no longer recommend allowable bearing capacity. We don't tell them the bearing capacity is 100 kPa and that's it. No, that's not correct. We need to tell them your ultimate limit state bearing capacity is number and your serviceability limit state bearing capacity is a different number. Okay, so a bit of history, but that's very important. Trigger why now geotechnical engineers should adopt to a limit state design. In early 2000s, structural engineers used to use the limit state design, which they are still using. But we, as geotechnical engineers, used not to use limit state design, and we used to use the working stress design, which means we don't speak the same language. And both as geotechnical and structural engineers, I don't want to say should, but they must speak the same language. So what happened out of problems, different levels of errors, and at some cases it went to like a very high safety issues. So it means we provide them for some things that they don't use and they don't understand when and where to use, and they provide us some things that we don't know how to use and when to use as well. That's why we got these two different, or this clear and distinction definitions: ultimate limit state and serviceability limit state. So what is ultimate limit state? Ultimate limit state is primarily concerned with collapse or failure mechanism of the structure. So if we did reach with the applied load to this case, it means the structure will fail. And from the geotechnical point of view, that should be our ultimate limit state bearing capacity, and that should be checked using the ultimate loads that we receive from the structural team. And these loads are usually the normal loads but factored, multiplied by a factor alpha. That's the key point. So we got the ultimate limit state loads, that what we use to check our ultimate bearing capacity. What about the serviceability limit state? Serviceability limit state is a condition or mechanism that restrict or constrain the intended use or function. I like the function way. So it does, if the building does exceed its serviceability limit state, it might not be able to perform the same functions that it used to perform before. So you might see like a huge gap between your elevator and the level or the floor level. So you might not be able to use the elevator and all of that. So occupancy of the structure. And it's usually associated with settlement or movement and deformation or deformations. And it should be checked using the service or the working loads that we receive from the structural engineers. So these are the loads that are not multiplied by alpha. So if you want to check ultimate bearing capacity, you need to get the ultimate loads, which is big loads multiplied by alpha. If you want to check settlement, don't use the ultimate limit state load, or don't use the ultimate loads, use the serviceability limit state or the working loads, which are the normal loads. They are not factors. They are not multiplied by a factor more than one, which is alpha. What kinds of load usually the structural team have? It's not a geotechnical part, but it's important to understand. Usually there are three different types of loads: permanent loads, transitory loads, and exceptional loads. Or sometimes they call that extreme loads. That's the H2 terminology. They call that extreme. So what are permanent loads? You can expect it's dead load, earth pressure, or surcharge. These are the loads that never go away. It's always there. Wherever a building is, you have a dead load. If you have a retaining wall, you always have earth pressure. If you have a building beside your building, so you always will get a surcharge. If you have an asphalt or a road above water, you will get a surcharge. That's most of the time it's exists throughout the lifetime of the building. What about the transitory? So transitory, that is, first of all, you will think about the life load and wind load. It's not always there. People are not always in the buildings. And load from differential settlement. Differential settlement does not happen always. It's one time or two times. And that's like differential, and that's like transitory. Exceptional are like the ones that's very high. So it's earthquake or collision if you are designing something else. Uh, or some now hurricanes, unfortunately in US. Okay, now it's something related to the settlement module, which is module number 2, but uh, it's important to just to know if you have a cohesionless soil, the soil settlement is immediate. Immediate settlement means you need to consider the maximum permanent and the transitory load. Both of them together combined should be considered, and that will be one of the ultimate limit state cases of loading that you will receive from the structural team. You don't need to count for the earthquake loads like all of the amount. Yeah, it's a big prob, it's a big thing, but at least you consider these two combined together. But for the cohesive soil or like the clay soil, it consolidates. It does not have immediate settlement. Consolidation, it's something time dependent. So it takes time to settle. So it doesn't make sense to consider all the transitory loads in your consolidation analysis. You can only consider a portion. What happens in real life? We usually don't do this. Even for cohesive soil, we take this for the settlement calculation, we take the serviceability limit state of both of them combined. But if you are doing that, you know that you have extra layer of like you have something backup, you have something to back you up. Because you know you are conservative. You know that the transitory loads are not always there, so it's not like a permanent load that will confirm the consolidation to happen over a certain period of time. Uh, and that's the practice. So that is the theory, and that is the practice. Again, being conservative in geotechnical engineering is preferred. And I like this slide because it shows you the difference between the limit state or the LRFD load limit state design in Europe and in North America. So in Europe, structural teams, they get loads. They factor these loads by multiplying by gamma or whatever by a load factor. So these loads does increase. And that are the loads that we receive for the ultimate case. They call it factored strength approach. Why it's factored strength approach? So they do factor the strength parameter. So they calculate C and Phi for the soil, and then they divide by a factor, which is FC or Fy. So they get a factor of the strength. So they, instead of phi equal 40, they use phi equal 30 to calculate the resistance. And they calculate the factored resistance that we calculated from the geotechnical analysis with the factored load that they calculated from the structural loads. And they make sure that the factored geotechnical resistance is more than the factored loads or the factored stresses from the structural team. That's why they call it factored strength approach. They factor the strength parameter, C and phi. We don't do that. In our LRFD, load resistance factor design, so we factor the resistance. What does that mean? It means we have C sub alpha, we have cohesion and friction, and then that's unfactored. And then we calculate the nominal bearing resistance or the ultimate bearing capacity. I never told you if you have a cohesion or friction, divide that by a number. I never told you that. I always tell you, okay, you calculate your Q ultimate and then you factor this Q ultimate. So you get your Q ultimate multiplied by factor alpha, which is less than 1. So you decrease your factor, your ultimate resistance. And that's what we call factored geotechnical resistance. So that's factored resistance is compared to the factored load, and that factored resistance must be more than the factored load. VIB notes. Values of phi and alpha are specified in each code, and that based on target values of reliability or acceptable probabilities. Phi and alpha is the factored load or the loads for the factors alpha, and the loads for the resistance for phi. That's calibrated based on the working stress design method, and that's really neat. It's something. It's like a different expression for the working stress design method, and it's calibrated to make sure that structural and geotechnical team use the same language. Eventually, phi and alpha are interrelated and rely on each other. What does that mean? It means you can tell me, okay, I'll go to ASHTO and get the loads, and then I'll go to the Canadian Highway Bridge Design Code CSA, and I'll get the resistance factor. That's not correct. and you will see a difference. You'll see a difference between the factored for the loads alpha and factors for the phi or the resistance in both the Canadian Highway Bridge Design Code CS AS619 and the ASH2 2020 Bridge Design Code. So don't do that. If you are working Canadian, you are working Canadian Highway Bridge Design Code. Use float factors from the Canadian Highway Bridge Design Code. If you are designing using ASH2, use just the factors for both load and the resistance from the ASH2 code. Don't use one from one code and the other one from a different code.